See, now let me check the first property. First property of our inner product, that is f. So that's nothing but integral 0 to 1 f of x into dx. So that equal to integral 0 to 1. What I have here is f of x whole square. Now we got an advantage. So now what I have here is a positive function. Okay, so this function is totally positive. Now you can see that when this is positive, when you integrate, then the result will be positive. This is always greater than or equal to 0. There is no doubt in it. And the next thing, what happens if this inner product is 0? That implies integral 0 to 1 f of x whole square into dx equal to 0. Yeah. Now we can apply the logic which was told by Ramadevi. Now since you have a positive function here, f of f square, so what you have is a positive function. It means the function is totally above the x-axis only, or on the x-axis. Now when you integrate it, so if it is 0, the result is 0, implies the function must be 0. Okay, so now here I can say that this is 0 if and only if f of x is identically 0. There is no other way. So therefore you can see that the first condition is satisfied. The first condition of our inner product is satisfied. See, I did not mention what is that function. That function can be anything. Whatever you take, it's integral 0 to 1, that function square will become 0 only when that function is 0. And let me check the next condition. So what is the next condition here? F plus g with h. That must be same as f plus h comma f plus g plus h. So let me check. So this is nothing but integral 0 to 1 f of x plus g of x plus into h of x. But we know one thing, integral is a linear operator. So using that we can write them separately as two integrals. But let me write this first. F of x into h of x into dx. Okay. I'd like to separate here itself. 0 to 1 f of x in g of x into h of x into dx. So this equal to inner product with f and h plus inner product with g and h. That's it. We proved the second condition. And the next third condition, what is it? Alpha into alpha u inner product with v must be same as alpha into inner product of u and v. So that is alpha into f comma g. So that is integral 0 to 1 alpha f of x into g of x into dx. You know that integration is a linear operator, so this alpha can be taken out. So this is alpha into 0 to 1 f of x into g of x dx. So this is same as alpha into inner product with f and g. Okay, and we need to prove one more condition, that is symmetric property. That is, if you take fg, that is integral 0 to 1 f of x into g of x dx, and this can be written as 0 to 1 since this function multiplication is commutative. We can rewrite it as g of x into f of x, and this is same as inner product inner product of g and f. That's it. Therefore, whatever mapping I define here, that is f comma g are mapped to integral 0 to 1 f of x into g of x into dx, which satisfies all four properties of inner product. Therefore, I can say that whatever we define here, this is an inner product. Okay, so it is clear that this clearly defines an inner product. Okay, but earlier you can see that earlier we defined one product, that is fg are mapped to integral of f plus g integrated over 0 to 1. This is not an inner product because it fails to satisfy that first condition. Okay, now let's look at one more example. Let's talk in terms of matrices. Inner product on 2 by 2 matrices. So let's say U is a matrix which is defined like this: U1, U2, U3, U4. Whereas V is a matrix where the elements are V1, V2, V3, V4. Okay. Now you define U comma V that equal to trace of U transpose V, this will be same as the trace of V transpose U. Can you tell me what is the trace of U transpose V? Can you see that this is nothing but U1 into V1 plus U2 into V2 plus U3 into V3 plus this. Okay, if you have a confusion, we can do it. Just you write the trace of this transpose of this matrix U transpose into V, so that is U1, U2, U3, U4 multiplied with this matrix V, V1, V2, V3, V4. So I'd like to know what is the trace. Trace is nothing but sum of the diagonal entries. So what are the first diagonal entry here? U1 into V1 plus U3 into V3. That is the first diagonal entry. And next, I'd like to look at the next diagonal, that is U2 into V2 plus U4 into V4. Okay, so now when you take their sum, so this sum is nothing but, that's it, U1 V1 plus U2 V2 plus U3 V3 plus this. Okay, now if you observe that this is nothing but, this is looking like a dot product on R4. If you rewrite this matrix like this as a column, as a row vector, U1, U2, U3, U4, whereas this one if you write it like V1, V2, V3, V4, okay, and dot product of these two is nothing but exactly this. So now you can check that there is no doubt it satisfies all properties of inner product. Yeah, if you have any doubt, you just check it. Okay, so now this clearly defines an inner product on matrices, 2 by 2 matrices. What happens if I take 3 by 3 matrices? Can I do the same thing? Think about it. Okay. Now let us try to define what is norm. Norm using this inner product. So let's say you take an element u from the vectors. So norm of u is defined like this. Norm of u equal to square root of, earlier we have written like this, u dot u, but this u dot u will be replaced with inner product of u and u, that is u comma u. Okay, so this is how the norm is defined. Norm of a function or an element in the vector space. And similarly, if you want to find the distance between the two elements, now let's define the distance between u comma v, that is nothing but norm of u minus v. But we know what is norm of an element, that is square root of inner product of u minus v with u minus v. Okay, so this is how you can measure the distance between two elements with the help of inner product. Okay. So one thing you tell me, I am taking set of all continuous functions on this interval 0 comma 1. Now the norm is defined like this. I mean, inner product is defined like this. Inner product of f comma g is defined as integral 0 to 1 f of x into g of x dx. This is how the inner product is defined. So can you tell me what is norm of f if, or let me write the function directly. What is the norm of x minus 1 by 2? And tell me, with the help of this inner product, tell me what is the distance between x minus 1 by 2 and x square. All that you need to use these definitions. You know how the inner product is defined. You know what is the function. Okay, let me do the first question. So the first thing is, first you're asking the norm of this. So first of all, let me calculate what is inner product of f and f. So that's what x minus 1 by 2 and x minus 1 by 2. So that's nothing but integral 0 to 1, you have x minus 1 by 2 whole square into dx. That's what, right? F into f is nothing but f square. And what is its integral? We know this is x minus 1 by 2 whole cube by 3. Limits are from 0 to 1. This equal to, when you substitute 1 by 3 is common. So 1 minus 1 by 2 whole cube minus 1 minus 0 whole cube. So what I have is 1 by 3 to 1 by 8 minus 1. Oh.
0 minus half.
0 minus, oh, okay, yeah. I wrote the reverse. 0 minus half. So this is 1 by 8. Something is wrong. Here I am taking cube, so minus 1 whole cube is minus 1, minus into minus, this is plus. So that will be 1 by 4, so 1 by 12. That's it. So now if you want the norm of this function, norm of x minus 1 by 2, that's equal to square root of this and that's equal to square root of 1 by 12. So which is nothing but 1 by 2 root 3. So that is the norm of x minus 1 by 2 under this inner product. Okay, so the next thing, let us try to find what is the distance between x minus 1 by 2 and x square with this inner product. So now I'd like to measure this, the distance between x minus 1 by 2 and the other thing is x square. So we know one thing, the distance between u and v is defined like this, norm of u minus v. So this is nothing but norm of x minus 1 by 2 minus x square. Okay, so let's do it. Norm of x minus 1 by 2 minus x square, that's nothing but square root of, let me do one thing first, let me find norm square and later I'll take square root. So norm square will give me integral 0 to 1 x minus 1 by 2 minus x square whole square into dx. Yeah, this time I don't have an escape, I have to expand it. So integral 0 to 1, I'll expand it this way, x minus 1 by 2 whole square plus x square minus 2 times x square into x minus 1 by 2. Yeah, we know a plus b plus c whole square formula, that we can use it, but I don't want to make it complicated. So now when you integrate the first guy, x minus 1 by 2 whole cube by 3, 1 by 3 into plus, and the next thing is x cube by 3 minus, you will get 2 into x cube, so integration is 2x power 4 by 4, minus into minus plus, 2 to cancel, you have x square, so integration is x cube by 3. The limits are from 0 to 1. Now this equal to, when I substitute 1 here, 1 by 3 into 1 minus 1 by 2 whole cube plus 1 by 3 minus 1 by 2 plus 1 by 3 minus, when I substitute 0, 1 by 3 into 0 minus 1 by 2 whole cube, and the rest is 0 anyway. Let us simplify this. So this is 1 by 2, 1 by 3 is it common? So I have 1 by 8 here, minus into minus plus 1 by 8 here, I get 1 by 4, this is one thing, plus 1 by 3 plus 1 by 3, 2 by 3, minus, I get 1 by 2. All that you need to take LCM, so the LCM is going to be 12, and you get 1 plus, and here you'll have 4, so 8 minus 6. So I get 3 by 12, that is 1 by 4. Okay. Now with this inner product, if you look at the distance between x minus 1 by 2 and x square, that is equal to 1 by 4. See, you try to understand. I am not saying that this is the standard distance between them. We define some inner product. With the help of that inner product, we are measuring the distance here. And one may measure the distance between functions in different way. For example, you have one function like this, and let's say if you have another function like this. Now someone want to measure the distance between them. then one may take the least distance between these two curves. For example, in mapping, like how do you know the distance between two villages? Like, yeah, there is a road path, you can simply measure that path, that's one thing. But in generally, what do? We actually take the distance between the shortest distance between those two, right? That we'll take it as a distance. Okay, but here I am not saying that this distance is same as this distance. Here, this is one way of looking at the distance, and this is another way of looking at the distance. Okay, I hope you understand what is an inner product and how to check whether the given function or the given mapping is an inner product or not. Okay, now we are going to deal with inner product spaces. It means a vector space with an inner product is called an inner product space. You have a vector space and you are including an additional structure on it. The additional structure is you are defining an inner product on it. So a vector space with an inner product is called an inner product space.